Hey everybody, just as a reminder, back what we did in term 2 was that we learned how to find the derivative of our inverse trig functions. And what we're going to do now is we are going to do that in reverse. We are going to take some sort of expression and we're going to integrate it back into arcsine, arctangent, or arcsecant. Now, before we get into that, we do need to know a little bit about the domain and range then for each of our functions. So up here at the top, I've got arcsine, and the first thing that we need is the domain for that. So just as a reminder, well, the domain for arcsine, that's the range of sine, and we know that sine is always between -1 and +1. So therefore, likewise, arcsine, its domain must be between -1 and +1. Then the range. Now, initially thinking of what the range is going to be a little tricky, but I have a way that I think will make it a lot easier for us. So I've got a bunch of unit circles over here, and I'm going to label this first one up at the top arcsine of x. The rule that we have for arc-trig functions is that we need one positive quadrant and we need one negative quadrant. Finding the positive quadrant is going to be very easy. That's always the first quadrant. So we know that arcsine is going to include that quadrant. Now we have to find a negative quadrant. So we should fill in the rest of these. Well, we know that arcsine is going to be positive in the second quadrant, and then it's going to be negative in the third and fourth. But we already know that the first quadrant is where it was positive, so we don't need the second quadrant. We only need one place where it's positive. Then to find which quadrant we're going to use that's negative, we just have to look at the one that is next to the quadrant that was already positive. So looking at these two, that means it can't be third quadrant, so therefore it has to be the fourth quadrant. That gives us then values that go from pi over 2, and we're not going to go all the way to what 2 pi is. We're actually going to use negative values here since it says it's negative. So we're going to go from pi over 2 to negative pi over 2. And actually, I just realized I'm using the wrong notation there because we can include those values. So it should be a closed interval rather than open interval. Okay, then the next one that we have is going to be arccosine. So just like with arcsine, its domain is -1 to +1. Then to find its range, we're going to do a similar thing that we just did with arcsine. Once again, we are always going to include the first quadrant. And then the second part is we also have to find the negative quadrant for cosine that borders the first quadrant. So if we fill in the rest of our unit circle, that's where it's positive and negative for cosine. We already figured out first quadrant is positive, so the fourth quadrant goes away. And the only negative quadrant we have that borders the first quadrant is in the second quadrant. So therefore, we know these values go from 0 to pi. And then our last one that we're going to do is tangent. So arctangent is a little bit trickier, but one thing that will help is if we remember what tangent normally looks like. And the graph of tangent is something kind of like that. And we can see that the y values there go from -infinity to +infinity. So likewise, that means our domain, this time we're actually not going to have a closed interval, it's open because it's going -infinity to +infinity. And then the range, well, for that one then, we need to do the same thing as what we did for arcsine and arccosine. Once again, first quadrant, always positive. We're always going to include that one. And then here's where it's going to be a little trickier now, because if we fill in the rest of the quadrants, well, the issue that we have, even though we eliminate the third quadrant because we already know the first is where it's supposed to be positive, we now have two quadrants that are negative that border the first quadrant. So I don't really have a good rule, a good explanation for this, but just the way that I've remembered it is it's always going to be the same as sine. So if we know that arcsine is going to be the first and the fourth quadrants, then we know arctangent is also going to be the first and the fourth quadrants. One other way that I could explain this as well is if we consider the graph of arctangent. The graph of arctangent is supposed to look something like that. And the only way that graph is possible is if we use the first and fourth quadrants. If we didn't, if we instead chose to use the first and second quadrants, well, this is what our graph would look like. And that's not a continuous function. We need arctangent to be continuous. So that is one other reason why I'm able to remember that it's the first and the fourth quadrants then for arctangent. Last part then, we just need to figure out what do we have for those values, and that is going to be negative pi over 2 and pi over 2 again. One difference with arcsine though, this is supposed to be an open interval that the parentheses are correct because tangent does not exist at pi over 2 and negative pi over 2. That's where the asymptotes are located. That's where cosine is equal to 0. So therefore arctangent can't exist at those either. Now the last thing that I have here is at the bottom, you may have noticed we haven't done anything with arcsecant, arccosecant, or arccotangent. And the reason is because those are more difficult to remember, and therefore I think it's a lot easier for us if we were to use the reciprocal. And I'm going to demonstrate here with cotangent. So I'm going to say, let's pretend that you are asked to find the value of cotangent of square root of 3. Well, instead of doing that, we can change that into its reciprocal, which is arctangent. Now the rule is if you do the reciprocal of the trig function, you must also do the reciprocal of the inside. So I'm going to rewrite that as 1 over the square root of 3. Now since this is tangent, we know that that is going to be sine over cosine. And in fact, I'm going to write it as arcsine over arccosine. And then we need to figure out what values from the unit circle can make 1 over square root of 3. Well, that occurs when sine is 1/2 and when cosine is going to be square root of 3 over 2. And if you think in the unit circle of where that occurs, well, that is going to happen then when x is equal to, let's see, that is at pi over 3. And there you go. So that is a demonstration then of how we can avoid worrying about arcsecant, arccosecant, and arccotangent, and instead we can just switch it over into its reciprocal. Okay. Now, again, back from term 2, we talked about the derivatives for the arc-trig functions, and here are all of the integrals that you need to remember that will go back into the arc-trig functions, or the inverse trig functions. Now, there's a couple things I want to point out. First off, you might be worrying that there's 6 of them here, but this is very important. You actually only need to memorize the 3 on the left side. These are the only ones you need to worry about, because all the ones on the right, they're just the opposite. So if you factor out the negative, then you can turn that integral into something that will become one of the inverse trig functions over on the left side. Now, the second thing that you may have noticed is that arcsine I should say, and arccosine do not have fractions in the front, whereas all the others do. I want you to be aware that is not a mistake by me. If you happen to consult the brief table of integrals in the back of the Thomas book, you will see that I have written down the integrals correctly. So I just wanted you to be aware of that in case you happen to notice and were wondering, is that a mistake? All right, now we're going to get into the questions where we are going to solve and find the antiderivative. So for this first one, we have the integral of 1 over the square root of 16 minus x squared. Well, one thing that we should do in order to identify how to integrate this is we should figure out if we go back to our formulas here, notice how every single one of them has a squared and u squared. U is supposed to be some sort of function in terms of x or in terms of t, whatever our variable is. A is going to be a constant. So coming back to this, I immediately notice, well, 16 is a constant, so that's our a squared. X, well, that's going to be u, and we've got a u squared there. So my first step is I'm going to rewrite this into something that looks a little easier for us to recognize. So I'm going to turn 16 into 4 squared, and then, well, we've just got x squared, so I'm just going to leave that as x squared. Now we can go back to our formulas and we can figure out which one does this match. So looking at the 3 on the left side, I notice that it looks just like the very first one. We have the square root of a squared minus x squared. So that means that this is going to integrate into arcsine. Then the next part is we're going to take, as this says here, u over a. So that means that we're going to have x over 4. And then finally, we're going to get a plus c. And there is the antiderivative for our very first one, arcsine of x over 4 plus c. All right, then for the second one, this comes out of the Thomas book. So it's going to be a little different and a little harder for this one. And the reason I say it's going to be a little bit harder is I notice inside the square root, well, that's supposed to be u squared minus a squared. But our u isn't going to be something really nice. If we label both of these, there's our u squared, there is our a squared, I can see then that u is actually going to involve the square root of 5. So I'm going to rewrite that. We got dx on top, we have x on bottom, we have the square root of 5 times x, and that is squared, and then it's going to be minus, and we'll take 4 and we'll turn that into 2 squared. Okay, then the next thing, well, we were supposed to have u squared here. And this is going to be integrating into arcsecant. But a problem is that we're supposed to have u in front with u squared in our radical. And currently, in our question, we don't have u in front. That's not matching with the u squared. So we need to make a change to this so it does match. We notice that u is supposed to be square root of 5 times x, so we're going to go ahead and just write in square root of 5 in the denominator. But of course, what we've done now is we have changed the value of our integral, so in order to cancel that out, we need to also put a square root of 5 up on the top. Once we have done this, now we have something that is going to match the form that we needed. Now this step isn't really necessary, but I'm going to show it anyway just because I think it helps you understand why we are going to get the answer that we get. I'm going to do u substitution now. I'm going to let u be equal to the square root of 5 times x. So therefore du will be the square root of 5 dx. Now we're going to make a substitution. So du is going to go on top. On the bottom then, we are going to get u times the square root of u squared minus 2 squared. And now this matches our equation for arcsecant perfectly, so we can just go ahead and write in our answer now. So we will get arcsecant, and I realize I forgot the fraction in front. That is supposed to be 1 over a, so that is going to give us 1 over 2. And then inside arcsecant, that was going to be u over a, so u over 2. We need a plus c. And the last thing is we just have to take u and put it back in, so we will get as our answer 1/2 times the arcsecant of the square root of 5 times x over 2 plus c. Okay, so here is another one. So again, my recommendation is that you should identify what is going to be your a and what is going to be your u. So we can see right at the beginning, whoops, not a cubed, a squared. And then we've got our x squared, which is going to be the u squared. So let's go ahead and rewrite this as 1 over 3 squared plus x squared and from the formulas earlier, this one then matches arctangent. So let's go ahead and we can change this. We can integrate this. This becomes then, well, our a value is 3, so it's 1/3. We have arctangent. We're supposed to get u over a, so that becomes x over 3. And we have a definite integral, so we're going to evaluate then from 0 to 3. All right, now the final part, we just need to put in 3 for x, put 0 in for x. I'm going to factor out this 1/3 and just keep it out in front. So we're going to have to evaluate arctangent of 3 over 3. And then we're going to have to do arctangent of 0 over 3. So we know for this first one it's going to be arctangent of 1. We know that the second part is going to be arctangent of 0. And this is going to be where you need to remember your unit circle. So I'm going to go ahead and I'm going to draw one here. Now, where arctangent is equal to 1, what we need to remember then, that's where sine, and actually more specifically arcsine, where arcsine and arccosine will be the same. So in the unit circle, we know that arcsine and arccosine, or maybe you want to think of sine and cosine, those will always be the same at pi over 4. And then over here in the third quadrant, and that is going to be 5 pi over 4. Now we need to remember, where is arctangent going to exist? Well, we always know all of our inverse trig functions exist in the first quadrant. Arctangent does not exist in the third quadrant. It's positive in the first, it's negative in the fourth. It does not exist anywhere else. So that means then that arctangent has to be equal to pi over 4. Because that is the only place in the unit circle where it exists and where sine and cosine are the same. So we're going to get 1/3 times pi over 4. And then we know that arctangent of 0 is just going to be 0. Again, that's going to be sine over cosine, so wherever sine is 0, and we know sine is 0 here at 0, and you could think of it as 2 pi as well, but arctangent has to be between negative pi over 2 and pi over 2, so that's why we're going to say it's 0. And then the last part here is that we just know that we have to simplify, and that gives us pi over 12. All right, so here are 2 questions that I want you to try on your own. I want you to pause the video here, give them a shot, and then when you are done, you can start the video again, and I will demonstrate how to answer these. Okay, so now that you have tried these, I'm going to demonstrate how to solve them. So that first one, well, it turns out that this is actually similar to a previous question we did. We've already done the integral for 1 over the square root of 16 minus x squared. However, if you've forgotten, I don't mind showing it again. So we know that we've got a squared first, and then we still got x squared there second. So let's go ahead and rewrite this. 0 to 2 root 3 of 1 over, and that's going to become 4 squared minus x squared dx. And from this, I can tell that this is going to integrate into arcsine. So we will go ahead, rewrite it as arcsine of x over 4 because it's supposed to be u over a. And then we have to evaluate that from 0 to 2 root 3. So if we go ahead and put those in, well, if we put 2 root 3 over 4, that means that we're going to get root 3 over 2. And then if we put in 0, well, of course, that's just arcsine of 0. Okay, now we need to figure out what are these values for arcsine. So again, we're going to need to make ourselves a unit circle. Arcsine exists in the first and the fourth quadrants, just like arctangent in the previous example. So if we're trying to find where root 3 over 2 is for arcsine, we know that that is going to be up here, and it also is in the second quadrant. But since we've already shown that it only exists in the first and the fourth, we can't use the value in the second quadrant. We can only use the value then that is in the first quadrant. And that occurs when we have pi over 6. All right, now that we have figured that out, or I'm sorry, that's not pi over 6, that's pi over 3. So we have pi over 3, arcsine of 0 is this value right here. That's going to be at 0. And this first one then, the answer is pi over 3. Okay. Then for the second one, let's again label. We've got our x squared there in the front. We know we've got a squared there. I'm going to rewrite this. We've got negative 9 and negative 6. Up on top we have 9, and then we have x times the square root of x squared minus 3 squared. And in fact, there's one thing that is missing from this. Well, not missing, I should say, but one thing that we can do to simplify is I'm going to take that 9 and I'm going to move it out in front. Because now the integrand matches one of our formulas exactly, we can now rewrite this as 9 times, and hopefully you're starting to remember now that this is going to be arcsecant. So we need to start with 1 over the a value, so 1/3. Then we're going to do arcsecant. It's got to be u over a, so u over a is going to give us x over 3. And then we have to evaluate from negative 9 to negative 6. All right, we're going to put these values in. I'm going to go ahead and simplify the 9 and the 1/3, so that's going to give us a 3. Then if we put in negative 6, that is going to give us negative 2. The second part is going to give us negative 3. Now we're going to be able to simplify part of this. The first part, arcsecant, this is back what I told you way at the beginning. Whenever you happen to have one of these trig functions and it's not, if it is not arcsine, arccosine, or arctangent, it's going to be a lot easier to just turn it into a reciprocal. So for arcsecant, let's go ahead and turn it into its reciprocal, which is arccosine. And if we do that, the inside must also turn into its reciprocal, negative 1/2. And I'm going to go ahead and do the same thing for the second one. So I am looking at the first one then. We need a unit circle again in order to solve that. So where cosine is equal to -1/2. Well, if we think about it, we know that cosine is going to be negative in the third quadrant. Excuse me, it is negative here, and it's also negative in the second quadrant. And then if we think of where cosine happens to exist, or arc cosine I should say, we know it is in the first and it is also in the second quadrant. So that tells us we want the value that we can find in the second quadrant. We do not want the value in the third quadrant. So, therefore, if I move this out of the way, we will have 3 times, and that value over there is going to be 2 pi over 3. And then the second part, we actually can't calculate that. I hope you recognize that -1/3 does not is not one of the values in the unit circle that we know. So we cannot simplify that last part. It's just going to have to stay as it is. And therefore we have our answer. Or you could, if you wanted, you could simplify that a little bit more, and we could write this as 2 pi minus 3 times arc cosine of -1/3. That would also be acceptable. All right, so that was everything. I hope you were able to make it through all of this. This is the assignment. Right now, my answer key actually has the full assignment. I've decided to break it up into 2 parts just to make it a little bit easier. Please note also, this is officially due on Thursday. So if you have any questions, please just contact me on Schoology or email me. And have a good day, everybody.